Hello everyone, my name is Kathan and today we'll be discussing the problem Grey Code from the Introductory Problems of the CSES Problem Set. Let's begin. Let me read out the question for you. A Grey Code is a list of 2 power n bit strings of length n. And I guess this you already know. If you have a length n string, all the possible number of bit strings are 2 power n. I guess this we have already discussed in one of the previous videos. It is called bit strings. Maybe I'll attach it in the I button above. Where any two successive strings differ in exactly 1 bit, which they call that their Hamming distance is 1. So if two successive bit strings differ in exactly 1 bit, then we say that Hamming distance is 1. Right. So here if you see the 2 bit strings only differ by 1 distance, that is to go from 0 0 to 0 1, only one bit has to change, that is this 0 bit. To go from 1 1 to 1 0, only one bit has to change, that is this 1 has to change to 0. Right. So all in all, like, what they're asking is they are asking one possible reordering of 2 power n bit strings where two successive strings differ in exactly 1 bit. That's what they're asking, right? So Grey Code is simply, you can say, a reordering of all the possible bit strings where the Hamming distance, or you can say the successive strings, differ in only 1 bit. That's what this means. A task is to create a Grey Code for a given length n, that is, give me that reordering of all the possible 2 power n bit strings in which the Hamming distance between two successive strings is 1. Fine. The only input is simply integer n, and we have to output 2 power n lines that describe the Grey Code. Fine. So that I guess we already cleared out. We can print any valid solution. Fine. And the constraints is simply 1 to 16. So I guess since we have to do an exhaustive enumeration here, right? So this is what it says. If constraints is pretty less here, 16. So even if you do a brute force enumeration, that is, you go and try to enumerate all the 2 power n bit strings here, it will work. Why it will work? I'll show you now. So first things first, like you can see here that n is less than 16. And how many bit strings can you have for n equals to 16? They will be 2 power 16. So even if you do, let's say, brute force enumeration, try to enumerate all the possible bit strings. Of course, we are looking for one of the possible reordering, but even if you try to generate 2 power 16 bit strings, this time complexity, like, can you convert into 10 power? I guess you can. We have discussed it, the conversion from powers of 2 to 10. So this will be 10 power 16 divided by 10 into 2. So this anyway, even if I consider this 20, it will be less than 10 power 6. So you definitely can do a brute force enumeration. Right. So definitely you can just try to enumerate all the possible bit strings and return that one of the possible reordering in which the distance between two successive values is 1. Fine. There's one little thing I expect you before you start with this discussion, like watching this discussion, that you know how to convert between decimal to binary numbers. Because like if I try to explain that as well, this video will become very long. So maybe what I'll do is I'll attach a blog which explains you that concept. Fine. So maybe you can read that if you don't know it, and we can continue. Fine. So like if you have, let's say, 2 bits, what are all the possible, you can say, binary numbers you can generate? They will, of course, you have 2 bits, right? So for this position you have 2 options, this position you have 2 options, right? So I guess this also we have discussed a lot of times. Either you can put 0 1 here or 0 1 here. So you will have binary numbers from, let's say, 0 0 0 1 1 0 1 1. So if you have n equals to 3, similarly you will have binary numbers from 0 0 till 1 1 1. So I guess this is one fact about binary numbers. Like if you have, let's say, some n equals to k bits, you will have, you can say, the binary numbers, binary representation of numbers, decimal numbers from 0 to 2 power k minus 1. So for n equals to k bits, you can have a binary representation of decimal numbers 0 to 2k minus 1. This I'll show you. So if you have 2 bits, you can have a binary representation of numbers 0 till 3, which is what? 2 power 2 minus 1, 4 minus 1. For n equals to 3, you can have binary representation of numbers from 0 till 2 power 3 minus 1, which is what? 8 minus 1, 7. So this fact is important. When you have n equals to k, you can have a binary representation of decimal numbers from 0 to 2 power k minus 1. With this clear, let's see some Grey Codes. Let's try to establish the significance of Grey Codes before we actually go in solving it. For n equals to 1, that is, you only have one place. Like the only possible bit strings are 0 and 1, right? So in other words, you can just represent binary numbers for decimal numbers 0 and 1. So this is the binary and this is the Grey Code. Now there's nothing special here because binary representation and Grey Code representation is looking same. But all that matters is to go from one number to another number, you only have to change 1 bit, the Hamming distance to be 1. Fine. The n equals to 2 case is a little bit interesting. So for n equals to 2 case, you can have, you can say, all zeros till all ones in the binary representation. So you will have a binary representation for all the numbers from 0 to 3. Oh, sorry, I guess it was only 2 bits, right? So you will have binary representations for numbers in range 0 to 3. So these are the decimals and these are the binary representation for it. Fine. Now notice one thing here. So in this gray code, if you go from 0 to 1, you only have to change one bit. So this is actually same as this only, nothing complicated here. So like this part is same, fine. But now one interesting thing, if you want to go from a gray code 1 to 2's gray code, you only have to change one bit, right? But what happens in binary? In the binary representation of 1, if you want to go to 2, how many bits needs to change? See, you have to first change this bit to 0, right? And then you have to change this bit to 1. So 2 bit changes are required here. But in gray code, you have to change only 1 bit. Now, why does this matter? Like, why is this important? Let's say this 1, 2, 3 are the volumes of some analog device. Now, if you are representing the numbers in binary representation in the circuit, what will happen is when you try to increase the volume from 1 to 2, you will have to change 2 bits, right? Now, what can happen is from this 0 1, you can temporarily go to 1 1 and then it will be changed to 1 0, right? So due to this, there can be, you can say, temporary errors during transition. But in gray code, if you go from volume 1 to volume 2, you just have to change one bit. Right. In this case, from 0 1, you might go temporarily to 1 1, that is volume 3. So you can say there will be a sudden spike in the volume and then it will go back, right? So you'll try to increase volume by 1 point, but temporarily it can get increased to 2 points and then it will come back to 2. So this is a problem, right? So this doesn't look good. So that's one reason why gray codes are very useful. There's one more reason, so maybe I'll just open this tape. So there's an expert from ChatGPT only I have taken. So gray codes are needed because they reduce errors during transitions, which I showed you, right? So there will be some temporary errors if you just use binary representation. They simplify logic design, so this has something to do with the digital logic circuits. So this maybe you will know when you study that digital logic circuits course. So I'll leave that when you study that, so be patient. And then save power. Why save power? Like, of course, if you are changing multiple bits to go from one number to another number, it's gonna consume more power. It's not efficient. I'll show you one example. Let's say you try to go from 3 to 4. So how many bits are changed here? 1 bit, 2 bit, 3 bit. 3 bit changes. But the 3's gray code, if you want to go to 4's gray code, only 1 bit is changed. Which bit? This bit. So this is of course more efficient, it saves power. So gray codes are very important. That's what I was trying to stress. Now let's look at gray codes for n equals to 3. So n equals to 3, how many numbers can you represent? You can represent numbers from all zeros to all ones. So this is what? 0 and this is 7. So you can represent numbers from 0 to 2 power n minus 1 here, which is 7. Fine. So again, you'll observe one thing. If you go from 0 to 1's gray code, only 1 bit has to be changed. If you go from 1 to 2's gray code, only 1 bit has to be changed. If you go from 2 to 3's gray code, only 1 bit has to be changed. Similarly, from 3 to 4's gray code, only 1 bit has to be changed. For 4 to 5, again 1 bit has to change. For 5 to 6, only 1 bit has to change. Similarly, from 6 to 7, only 1 bit has to be changed. So I guess I have made it clear that gray codes are very efficient and they're very important. Now, but how do you solve this question? That's the main thing, right? Why you're here. Now, gray code is a very interesting property. Now, there's one more, there are two ways to solve this question. There is one formula where you can directly convert from a binary number to gray code, but I don't think you'll learn much there. Instead, let's build the solution step by step logically, right? So, gray codes have an interesting property which they call reflective property or mirror property, which you can exploit. If someone just tells you that gray codes have a reflective property, then maybe you can solve this question from ground up. So what is this reflective property is, for n equals to 1, the possible gray codes are simply 0 and 1. Fine. Now to get the gray code for n equals to 2, what you do is, you take the gray codes for n equals to 1, you take these gray codes, put a mirror here. If you put a mirror here and try to look from the bottom, so you are trying to see here, what do you see? Like if you see from the bottom, you have 0 1 and you try to look at the bottom. So if you try to look at from the bottom, you will get here 1 0, right? So you are trying to look at the bottom, so you will of course first see 1 and then you will see 0. So you do that. So you take the gray codes for n equals to 1. To generate the gray codes for n equals to 2, you take the gray code for n equals to 1, put a mirror, right? So this is the reflection you will get, like 0 1's reflection is 1 0. You append zeros here, append ones here. So you append zeros in this half and append ones in the mirrored half. Fine. If you want to get gray codes for n equals to 3, what you do is you take the gray codes for n equals to 2. So these are the gray codes for n equals to 2, right? So these are okay. These are the gray codes for n equals to 2. You put a mirror here, and try to look it from the bottom. So now you have a mirror and try to look it from the bottom. So if you try to look it from the bottom, what do you see? You see here 0 1 1 1 1 0 0 0. In a way, mirroring is just like reversing, right? So if you put a mirror here, it's like you are just seeing it from the reverse manner. That's what you're doing. So this reversed is what I have put here. Fine. So you put a mirror here and then append zeros here, append ones here, append ones here. So this is exactly same. Like you can verify for yourself. This is what is happening. So this is the reflective property. So if someone asks you gray codes of n equals to 4, what are you gonna do? Take this guy, right? Maybe I'll just use colors here. Take this guy. Take this guy here. Mirror it. Put a mirror here. In other words, if this was let's say gray codes of size 3, you just take a mirrored version of it. So maybe just 3 power r. Basically just reverse the list, right? So if these were the gray codes, if to get a gray code of size 2, you take the gray codes of size 1, reverse them in a way, right? 0 1, you made it 1 0, reverse them, append zeros, append ones, right? So if someone asks you generate me any gray code, let's say someone asks you generate me a gray code, let's try to formalize a bit now. You can already see some pattern emerging here, right? So if someone asks you a gray code of size here, let's say 5, someone asks you for, let's say this was n value, n equals to 5, what do you need? You actually don't need to think very smartly. What you can say is this: you generate me a gray code of size 4, that is, you generate me a gray code of size n minus 1. I'm gonna take them, okay, I'm gonna put them here. Then in the bottom I'm gonna put their mirrored version. I'm gonna just append zeros here and append ones here. So this is gonna give me the gray code of size 5, gray code with number of bits 5, that is 2 power 5, 32. But how do you generate gray codes of size 4? You don't need to be very smart here. You just give me gray codes of size 3. You give me gray codes of size 3. I am gonna take them, put their mirror below, that is this reverse version of them, append zeros here, append ones here. But how do you get gray codes of size 3? Don't need to think much. Give me gray codes of size 2. I'm gonna do the same logic. Put them here, put the mirrored version here, append zeros here, append ones here. But how do you get gray codes of size 2? No need to show any smartness. Just give me gray codes of size 1. No, sorry, gray codes where n equals to 1. Now this is the base case. You already have these gray codes. So these gray codes are 0 and 1. So what have we done? Like, this is just a recursive logic, right? So if I write the pseudocode here, what you need is, if someone asks you to generate gray codes for n bits, so here they're asking you to generate 2 power n gray codes, what you effectively have to do is, you just generate me gray codes for n minus 1, right? N minus 1. So this you can generate for GC of n minus 1, right? So you assume that GC is gonna return gray codes of with all the possible gray codes of size n minus 1 bits, and what you have to do is, you take this GC minus 1, you append zeros to this GC n minus 1, right? Then you append this, and then you append ones to the reverse of this GC n minus 1, right? And this you can return. So this can be easily done, right? You just have to traverse it. So if someone asks you to generate gray codes with n bits, you first generate the gray codes with n minus 1 bits. You append zeros to the gray codes of n minus 1, append ones to the reverse of, to the reverse of gray codes of n minus 1. So effectively you have just mirrored it, and the mirrored version of appending 1, and this you can return. This you can happily return. And what is the base case? How do you stop this recursion? You stop when n is 1. To stop the recursion, you should always think about, you can say, the smallest possible value or the largest possible value. So here, since we are going from top to bottom, you will think about the smallest possible values. For n equals to 1, all the possible gray codes are simply 0 and 1. Right, so I mean the question is done and dusted. This is a pseudocode. Now all that remains is to find out the time complexity. Now to calculate the time complexity, there are two ways. Either you can derive the recurrence or just look at this recursion tree. So what is happening here is you will start from, you can say, generate gray code of n. Then you will need help from gray code of n minus 1. Then to generate gray code of 4, you will need a gray code of 3, so on and so forth. So like what you have is eventually the depth of this recursion tree is order of n, right? So the depth of this recursion tree is order of n. And at every level, how much amount of work you are doing? See, to generate GC of 5, any which way you will have to process 2 power 5 numbers here, right? So the mirrored version, you can say here you will have to process 2 power 4, and here you will have to process 2 power 4, right? So any which way you will have to process in total 2 power 5 numbers. Similarly, if someone asks you to calculate the g power 4, what you'll have to do is you will need g power, like gray code of 3, right? And then this will be 2 power 3 numbers, and this will be 2 power 3 numbers, right? So to find GC of 4, you will need to totally process 2 power 4 numbers. Any which way, at every level here, so there are order of n levels here, the depth is order of n, and every level you are spending 2 power n time. So this is the time complexity, n into 2 power n. This is the time complexity. This is one way to look at it. Just look at the recursion tree, right? So how much work you are doing. So at every level, so there are n levels. At every level, you will have to generate 2 power n gray codes. Simple, right? So that's why the time complexity is n into 2 power n. And what is the space complexity? You are generating this, like, so there is some temporary storage required here, and at the last as well, like it can go as high as 2 power n. So if this is time, the space complexity will be order of 2 power n as well, right? Since you are gonna generate those 2 power n and then gonna return them finally. So 2 power n space complexity is required here. Now you might argue that this is the space used for output, but I would say if you are returning it from the function to the main, then you are using some extra space. So 2 power n for storing the output, if you will. And finally, there will be some recursion stack space required as well, right? Because these functions are being called. GC of 5 calls GC of 4, GC of 4 calls GC of 3, so on and so forth. So this again will be equal to the depth of this recursion tree, which is order of n. So 2 power n plus n, but the dominating factor will be 2 power n. So the space complexity is 2 power n, time complexity is n into 2 power n. Fine. So I guess, yeah, I mean that's about time and space complexity. And if you have understood the video till now, please comment understood in the comment section right now, and then we can move on to the code. Alright, so here's the code. I'm taking n as input. Then I'm initializing this vector of string gray code where I'll store the output, right, final output. Then I'll call this recursive function, generate GC of n. So just generate me gray codes with n bits, and then I'll go through all the gray codes and just print them. Right, so let's just go through this recursive function, generate GC, which is the main function here. Generate GC. So what we do is we just generate gray codes of n minus 1. Then we find the mirrored version. Mirrored version is simply reverse of it. So this is what it is, right? I'm just reversing it. You can use the reverse STL function or just simply traverse G codes minus 1 from n to start and fill them. And then I'm gonna create gray codes n bits. Now how do you create them? Append zeros to G codes n minus 1 and append ones to its mirrored version. Now of course you can get away by not creating this mirrored array and just traversing this guy from reverse, but I just wanted to keep the code clean for you to understand. But you can of course do that by not using this mirrored version. As a matter of fact, let's give it an exercise. How are you gonna do this without creating this array? In which way doesn't affect the overall time and space complexity. Fine, it's just gonna increase a little bit space, but not that much. And yeah, I mean that's what we do. We take gray codes of n minus 1, append 0 to it, append 1 to its mirrored version, and these are the new codes. So new codes means the gray codes of size n with bits n. And base case, if n is 1, it's simply 0 and 1, right? So these are the gray codes with bits 1. Fine, I mean, yeah, that's about this question. Time complexity, I guess we already discussed, n into 2 power n, and space complexity is 2 power n plus n. So this is for the space, you can say to store the output. Why am I counting it is because here you are gonna generate temporarily all the gray codes. That's why the space is counted here. Fine. And then so this is 2 power n. This is not the space for this variable. It is the space for the temporary 2 power n gray codes that are generated. That's what I was saying in the explanation part. So that was about this question then. I hope you liked it. If you did, please give it a like and I'll see you in the next one.